This is our LM386 PA system circuit. As you can see, there's switching on the input and the output for DAC and microphone and speaker out. So we transition to the circuit. You can see this is our LM386 chip, gain control, and this is our volume control. And these are our switches. And our microphone is right here. This is the demonstration for the PA system made with the LM386 microphone.
Check. Mic check. 1, 2, 3. Mic check.
Alright, for the LM386 PA system, we have LabVIEW set up so that we have a total harmonic distortion as a percentage, output waveform, and the input waveform. We can flip these two switches right here to change the signal. And now LabVIEW shows a 0.2% total harmonic distortion, and that is the output waveform. We can also change the volume by rotating this potentiometer. Here we have our multi-stage amplifier design. This is a current mirror, and it supplies the current to this differential amplifier. From the differential amplifier, it goes a single-ended output into this level shifter circuit made with a PNP transistor. From that PNP transistor, we have a input buffer, or in this case would be an output buffer made with an NPN BJT. That's so we can take a high impedance output and change it into low impedance to make it easier to attach a output stage onto it, which is a Class B output stage. And then here is our 8 ohm load, which is our speaker load. We have our two input waveforms. Red is the input, blue is the output, and you can see the volts per division over here. You can see that all of our average power ratings, it's a little bit less than 50% efficient. This is the final product circuit. Here we have our transistors that make up our current mirror. Here we have the transistors that make up the differential amplifier. From there, it goes into this level shifter circuit right here. And then down to the common collector output buffer. And then it goes into the Class B output stage. And you can see all the white wires that I have over here. These are all signal wires, so that's where the signal's traveling. And you can see that the signal travels all the way into the output here, which connects to our speaker. Now we'll do the function check of our multi-stage amplifier. First of all, with this microphone, you can see our switches are to the left, which means that it outputs at the speaker and inputs at the microphone.
Check. 1, 2, 3. Check. 1, 2, 3. Testing.
Now we can go and pull up LabVIEW. We have the same setup as before, total harmonic distortion as a percentage, the output waveform, and the input waveform. Flip these switches. Our speaker is outputting a 500 Hertz waveform, and we can move this switch to the right to input that waveform into LabVIEW. It's saying right now there is about 0.5% total harmonic distortion, which which is not bad at all. We can also change the volume. For our unique application, we have included in our LabVIEW script a clipping threshold percentage indicator. And basically what this does is if your signal goes over a percentage total harmonic distortion, it will turn on an LED, this red LED right here, and also this Boolean LED inside of LabVIEW. It will turn it on to tell you whether your waveform is clipping or not. This is important because in a lot of audio recording, you don't want your signal to be clipped because it sounds bad. You want a nice, clean, and crisp signal. So right now we have LabVIEW outputting a 0.2 volts peak signal into our amplifier circuit. And I can change the volume using the potentiometer. So you can see as we go over about 10 volts peak, that's the limit of our rails. And you can see when it goes over 3% total harmonic distortion, that Boolean comes on. And you can also see the LED comes on.